Okay, let's start with the theoretical class today, okay? And that will be it. And then some admin first. Okay, so I just want to highlight at this point, here's where we are in the course. We have finished attractor networks or the hot field network, okay? All three phases of it. We went through the theory, then I introduced how do you implement that in a code using my example code, okay, which is a basic suggestion. You are free to use it or you can do your own, okay, and then specifically you do it in application for assignment 1, which we had a lab last week. Everyone was going around trying different ways of solving different parts of assignment 1. And the idea is that as you go through assignment 1, you actually implement the code and try to solve the problems, the steps, you get the idea of how to make a neural network from ground up, okay, and interpret the architecture and the activation functions from like a pure simulation paper, how to translate that into your own kind of code and how to use that in solving sample problems. And if you get it, then it shouldn't be too hard for you to then leap to real life data problems, right? So in the hot field network, we were interested in solving content addressable memory, and so here we are, and so that in class, when we try it out in our simulations, those are prepared exercises, but you can imagine how in real life situations you might be able to modify things, or whether you have some problems that actually fit the same similar hot field network problem, and therefore use the autoencoder, okay? So that was for attractor networks, and before we launch into this week's where we are at today, which is we're gonna move on to backprop. Any questions or final things about attractors or hot field networks? I think I might have mentioned that the hot field network is in a sense in fact it is a principal component analysis, okay? So it's like a hot field network is an attractor network, it's an autoencoder, and it is also doing actually principal component analysis, okay? We won't go into the details for that, but you think about it, right? Actually, what is it doing? And if you go back, if you know about principal component analysis, go and look it up. If you're not sure, you find that actually they converge in terms of how they solve problems, okay? Basically, dimension reduction, okay? All right, any final issues? Okay, if not, then assignment-wise, assignment 1 is already open in case you don't know, okay? So, and we went through that last week, part of it, but there's quite a bit more that you will need to complete on your own, and the due date will be on May 15th, okay? So please be working at it. And the good news is that next week is Labor Day, there's no class, so you can have that week and 2 weeks to sort of catch up and to work at the assignment, all right? And so then the assignment will be due on this date, May 15th, and on May 15th I will release assignment 2, which will then be for backprop. But actually I will be releasing backprop assignment or working at it similarly. So in backprop's second lecture, which is 2 weeks later, I will show you the code of how to implement backprop after we talk about the theory today. Okay. Then on the last week of backprop, we will again do a lab thing and people try out assignment 2, similar structure. Okay? All right. Okay, so that's where we're at. And then, so today we will talk about backprop. And for backprop, before I go into my part of it, again, to introduce to you, this is the Rumelhart chapter, and if you see the second author here is G.E. Hinton, is Geoffrey Hinton, is again a Nobel Prize winner, okay, and obviously he won the Nobel Prize for backprop, okay, because of his work in backprop, okay. So, and in fact, this is because of this guy, or at least, you know, this guy is a big contributor to all the ChatGPT and Gemini and whatever you have today, okay? So just to put things in perspective here, okay? So we are again working with a second Nobel Prize winning work. First one being Hopfield, and the second one being Hinton, okay? And so these are like very critical, fundamental neural networks concepts that you can see have large applications. Okay, that's why it's very important to learn them from the ground up rather than to just apply them from the tools. So if you had time to read through, and I strongly encourage you to do that if you haven't already, please read through those papers. And I think most of you will realize they are not easy to read at all. Okay, even I find it very hard to read. All right, if you find it easy to read, well, great. All right, congratulations. But I don't think they are easy ones. But I think we start now at whatever level we're at, and then as you go along over years, you read it again and again. I certainly have read it over and over again over the years, and each time you get a deeper and deeper understanding. That's how things work. Okay, so just introducing it to you guys, and hopefully eventually you will come back to it and you will learn more and more about it. And there's a 2025 video. As I said, I hope you have the chance to look at it before this class, so that maybe it'll be easier to digest certain things as I talk. As I repeat a lot of the things that we talked about in previous years, okay? And also the notes, which I will be using to sort of rehash again this year. So the content from previous literature is all here, okay? So please do take time to look at it. And then based on today, we might cover new things, or we might emphasize different things. That's the new video that will be up next week when the system posts it. All right, so that will be it. And then I will talk about theory today. So today, no coding, nothing, just theory. And then next week, we'll take a break. And then the second week, we will do the coding part. I will introduce you to the coding part using assignment 2. And then the last week will be the lab, where we will interact with the assignments and solve problems. Okay, let's start. Hey. All right, so with backprop, talking about backprop today. As the name implies, it has something to do with propagation. Propagation means propagation. Propagation means to spread. Oh, I'm using my Mac. Hang on this. No wonder it writes so much better. Where's the pen? Okay. Hang on, let me try. Yeah, I like this pen. Okay, as the name implies, it is to do with propagation. Propagation means to spread, right? Okay, like propaganda, right? Politics, you spread fake news. Okay, then after that, and in front of that you put back, means it's not just about I propagate, but I back propagate. So whatever I get, I sort of push it backwards. This is a very abstract concept actually, okay? But what does that mean? It's like the people who give you the information, you push it back to them, sort of something like that, okay? Backprop, snazzy term, very cool term, but what does it actually mean, and how does it work, why does it work, and how do we use it, all right? So first of all, essentially, we should note that this is a learning algorithm. Oh, I'm not damaging. Yeah, I'm not damaging it, so it's good. Okay, it's a learning algorithm. So in contrast to Hopfield network, well, actually, Hopfield network is a learning algorithm in the sense of that it is a Hebbian learning rule that Hopfield was trying to implement and then demonstrate that if you set up your network that way, you can get some memory, right? But the difference is that the goal for Hopfield was actually to achieve memory, okay? And in achieving memory, he had to use, or he tried to use, Hebbian learning to do that, okay? Here, when Hinton and team are trying to solve whatever problem it is, they were focusing not so much on any psychological concept per se, all right? Well, I guess they were, in the sense that they were trying to find out how to learn rather than some other concept, all right? So the focus here is about how does any intelligent system learn anything in the first place. So in Hopfield, he assumed that intelligent systems learn, and they learn by the Hebbian rule. And that was it, and showing that if you use the Hebbian rule to learn, you get memory. Here it's a bit more fundamental and go, well, how do you learn in the first place, okay? And why does learning work? How does learning work? All right, so that is a key question here. And the application is that if you have a network that learns, then essentially what you're trying to say is you want a network that pretty much learns anything, not just for memory, not just for perception in perceptrons, but to learn pretty much anything. And we'll come back to that concept a little bit, all right? And of course, we know that this is a learning algorithm, in fact, that is implemented in all current models, all current model applications that we know. LLMs, CNNs, DNNs, etc. I think I should choose this one. I don't want to spoil the board, just in case I get scolded. LLMs, okay? All LLMs now essentially still rely on backprop, okay? In a sense, and you will see, it is just about like I have some output, I have some error, and then I use that error into my LLM, okay? CNNs as well. CNNs are convolutional, so this is large language models, right? Large CNNs are convolutional neural networks. And DNNs are deep neural networks. We won't talk about them in great detail in this course. We will come back to these actually at the last lecture or so, but I'm sure you've heard of them, and I will tell you more details. They are just different kinds of architecture. But essentially, no matter what it is, all of these, they rely on backprop, okay? And so what are we backpropagating? Specifically, we are backpropagating error, as I said, okay? Error meaning that your network will do something, okay? And whatever it does, the world or us, we think, not satisfactory, okay? Please, you gave me A, but actually I want B, all right? Then that difference between A and B, that's error, okay? It's sort of like GLM, general linear model, right? You have your model fit, and then the part which is residual, the part that doesn't fit, okay? That's the part where the model fails, okay? So similarly, in backprop, we have the part where the model, the LLM, CNN, DNN, or whatever model, it fails. And actually, we want to use that failure to learn. So this is a good life lesson. You learn from making errors, okay? Hopfield is you learn by being right. Okay, you reinforce when you are right, so to speak, or you like what you like, and that kind of deepens your your representation. In backprop, you learn from when you are wrong. Okay, so very cool, right? And in fact, if you do psychology or if you do neurobiology, this is the heart, the core of reinforcement learning, right? That the animal or the system does something and you either reward it for it, you reinforce it, or if it's undesirable behavior, you punish it, so which is negative reinforcement, right? So these are what reinforcement learning is. And if you know the reinforcement learning literature, you will know that what's very important, the term that is holds all of reinforcement learning together, or the idea of it is that reinforcement learning or backprop learning from error operates according to the delta rule. The delta being this thing here, this is delta, okay? And where delta is equals to some target output state, a vector, okay, of outputs. You can treat it as a one-dimensional vector of a binary n-bit word, just like what we were dealing with in Hopfield. So we want it to say cat, and so it says cat. So let's say this AT is whatever that n-bit word, and it represents the idea of cat, okay? But that's what we want. But the network actually gives us its actual output, which is J. Again, I is the upstream and J is always downstream relative to I, right? So, but T here is target. So there's a distinction here. Downstream output, okay, versus the target. So we all call this the target output that we want, or some rule requires, some context, some game requires, okay? But AJ is the downstream output, and we call it actual output. Actual output, okay? So let me flip this around. And if you compare the two, simply you do a contrast, right? That's what delta represents. The delta rule means that whatever it is, we take the delta and we sort of consume it, we backprop it so that the network learns from the error. Other ideas of what a target output might be, desired output, wanted, goal, what else? Reference, yeah. You get the idea. It's a target, something that we hope to get, or a system hopes to get. And essentially, by doing this, by doing the reinforcement learning and delta rule, the goal of delta rule, the goal is such that okay. That we want the error to essentially be 0, right? And by that, we mean that the output of the network is exactly what we want, correct? And that translates to what we want is to minimize delta. No problem, very easy. Okay, so a brief note here is that there are other similar ways, many overlapping terms and fields that really rely on the delta rule at heart. So we talked about one, which is, so the delta rule is very well known. That's a terminology, okay? And reinforcement learning, we mentioned that just now. It is also error-based learning. and this one you may or may not know, Rescorla Wagner rule. In psychology, in behavioral literature, behavioral psychological science at that point, where they were very interested in how human beings learn. Rescorla Wagner was actually one of the first few to propose something like the delta rule, okay? And then Hinton and the computer science people sort of, and Barton and Sutton and Bartle, sorry, okay? John Sutton, Bartle. Oops. Okay. These are psychologists. These are computer scientists. Okay. Sort of, I don't know if they were talking to each other or they're not listening to each other and then they came at it independently. But around the same time, they came up with the delta rule. All right? Or at least the idea that for any system to learn, you learn from error. And when error is specifically whatever the system gives you compared to whatever you want the system to actually give you. Okay? Rescorla Wagner did it from a human behavioral psychological way. And Sutton and Bartle came at it from a computer scientist way. And I mean, we don't really care, but right now, today, what we have is this Hinton way, okay? All right? And you might also know this term and that's sort of these two streams integrate into there's this notion now of temporal difference learning. Okay, TD, all right? And this is a class, this is a kind of an evolution of the Rescorla Wagner and the Sutton Bartle and the integration of that. And John Sutton is still alive, and they're still very much actively engaging, and they know very much about temporal difference as well, because what temporal difference is actually in a neurobiological system, real, not a computational science one, but you actually put electrodes in, let's say, your dopamine neurons, okay? They have target brain systems, and they found that the dopamine neurons, or the dopamine system, all right, not just that, but that is one of the systems we know very well, okay, does temporal difference learning. And the key operation here is it's about a difference, which is delta. However, the delta has a time component, okay, which is that it has a future kind of state, right? It expects the future to be something, but the current experience reward falls short or is not yet what the future is, right? Or what the future it thinks should be. And this difference, this temporal difference, is what the system learns. And many scientists use this setup, these models, and John Sutton actually works with some of these people, and they found that it really accounts for our dopamine systems, like even the electrode spiking and all that. So it's remarkably well performing. So which suggests that they've hit on something, a very neurally plausible model, right? That if you sort of modify the delta rule and all that, and you incorporate the notion of time, future time versus current time, the difference in that, and then you tweak it, you actually can create the same neural responses that we measure from, let's say, dopamine, striatum, all these kinds of neurons, all right? So I just want to bring this out. We're not going to worry too much about this, all right? But there is some neural plausibility here, and the idea of bringing this out is because this one is about the dopamine system. In the in the Hopfield network, we talk about content addressable memory, right? But we never, and we say that it's a psychological phenomenon. Our memory has repetition effects, has a kind of fuzzy trace effect, like you give it a distorted trace, it falls into one of the learned traces. These are behavioral phenomena. Here, there's a neural phenomena, okay? It's a neural candidate, all right? But we won't talk too much about that. I just want to highlight that there is work being done in this domain, and you can feel free to look it up, okay? Okay, so just to put things in better perspective, recall that we started with the very first thing that we talked about was the single layer perceptron. Right? And we used it to solve logic gates. And in fact, it had to be such that the input has a linear mapping to the output. Right? That's and or. Okay? And it's linear because you don't have weird situations where you have to have a deeper hidden layer. Okay? That's talking about the single layer. If you want to solve nonlinear problems like XOR, you find that you need something else. Okay? So hold that, we will come back to that. Then from here, we went on to the second case where we have talked about autoencoding. And this was the Hopfield network. The Hopfield architecture, where every neuron is connected to every other neuron except itself, all right? And implementing Hebbian learning rule, okay? And we use it to solve content addressable memory, CAM, all right? And in this case, we have input states rather than input states resulting in output states, rather than specifically that you have an input layer and then you examine the output layer, all right? And this we will call embeddings. The mappings are embeddings. How the input and the output are mapped to each other, that's sort of an embedding or an encoding, okay? All right, so then finally, we are now, here's where we are now, number 3, okay? And we will be, so the single layer perceptron solves some problems, only linear mappings. The autoencoding solves some problems, which is that I want to encode myself. Remember, the goal for content addressable memory is that the output is equal to the input as much as possible, okay? All right, and so these solve some input-output mappings, a certain class, all right? This is a linear class. This is a self-encoding class, self-encoding embedding types of class. Here now, this is a very, very bold claim. This network that we are going to deal with, all right, has a proposition that this network, this number 3 network, okay, can do anything, literally. okay? And what we mean by do anything is that, so we're going to do an error backpropagation network, okay? The candidate here, or use this error backpropagation learning rule rather. And specifically, the network that we are going to deal with is a multi-layer perceptron as well. Okay, so it's a MLP. All right, and essentially, when we mean that it can do anything, what we mean by that is that the MLP can map any input into any output. So here we are limited to linear cases. Here we are limited to self-auto-encoding cases. Here we should be able to do all of that and more. So, and one of the assignment questions in assignment 2 will be, can you use this to do this? Certainly you can use this to do this. Well, can you? You can test that. But this can do this, and this can also do more than just this. All right? So we'll get to that. But that's the claim here. That's the so-called proposal here. All right? Which is why you see now you have ChatGPT, Gemini, seemingly, literally can do anything, right? You haven't given it arms and legs yet, so it cannot move. But theoretically, if you do the coding right, you put some arms and legs, it can move and stuff, right? It can see figures, pictures now, right? It can hear sound, just no touch yet. Well, you can train it to do touch, okay? So getting there. In a few years' time, we're going to have an Android standing here and be like, you'll be able to really talk to the person, talk to the robot and all that, right? Some people think it's scary. It's kind of cool. If it can make it help me clean my dishes and cook for me, that would be great. I just have, please cook something for me and clean my house. Okay, so so if we get the transition there from the first model, and we've been building it up, right? So I hope you appreciate in this class, we are going from more fundamental levels, simpler levels, and then we're making the case to see how things evolve and how things actually become more and more complex, but more and more complete. So in backprop, okay, as always, if we want to solve the problem in a formal way, we have to instantiate a hypothesis or a goal. Okay, the goal, as we said before, is to minimize delta. So we want to create a model. If the claim is that if we want to have a model that can map anything to anything, the claim is that if I have a model that does backprop, and by that meaning that the goal for backprop is to minimize delta, then this network, if it does backprop, can map anything to anything. That's the hypothesis, right? H naught here. That in backprop, the goal is to minimize delta so that for the purpose of to map anything to anything. This is a statement. This is the hypothesis statement. I know we know LLMs, we know ChatGPT, we know Gemini, all right? But some smaller level, smaller pieces of code that you can probably see in Python already, a function like character to vec is a mapping, is an embedding, right? I have a character like ABCD, CAT, right? CAT, I feed it to character to vec, it gives me some token, some other representation, but it is a mapping between CAT to some vector state. I have then word to vec. right? And then I have concept to vec. I have many, many things, all right? You can do this. Which essentially what we do, right? You have your fundamental characters. They map onto some output, whatever it is, doesn't matter. That output map onto some, you feed it to a word to vec, it maps onto another set of outputs, and these sets of words up to vec outputs, you map onto concept net, okay? It's mapping anything to anything and itself recurring and all that. You can do it that way, all right? And so this is proposed by Hinton, all right? As I mentioned before, okay? And the idea is that therefore we have to use, because we want to minimize delta, we have to use delta to achieve this goal. All right, to achieve this goal. Can it achieve this goal, and how does it do that? And this is where we want to get into a set of proofs. Let me see. I'll highlight the problem a little bit more first. I'll flesh it out a little bit more formally, and then after we'll have a break, and then after that we'll go deeper into the proof. So we're going to start now to prove BP backprop, or at least to show that it does what we want it to do, okay? The problem set is that we want to map any set of inputs arbitrarily, okay, to any set of outputs. Okay, set of outputs. Okay, now this is very critical. Arbitrarily is very important. In hot fields, all right, you all were playing with it playing around with it last week. There was some cases where the network performed pretty well, and then some cases where some input patterns where the network started to fail. This is apart from the distortion, or the distortion was part of the testing. But remember that when we tested the Walsh functions, which were orthogonal, it seemed to be okay. And then we tested some other orthogonal functions, seemed to be also okay. But then when you start to do your own random network and all that, starts to have some difference. I hope you saw that, okay? And if you follow on through the rest of the exercises where you train things that, you test on things that have not been trained before, etc. and all that, right? It seemed like the network was sensitive to the kind of information that was being fed to it. It can remember certain things very well, but certain things it cannot remember so well, right? So in other words, it's not arbitrary. It depends on what kind of content you give it. The content will determine the network's performance. Here, the idea here is arbitrary. It doesn't matter what the content is, it can still learn it. Okay? And this will be in contrast to the last network we will talk about, where it's absolutely not arbitrary at all. There's really, really some deeper meaning to the stimuli. All right? But here, first, the claim here is that it can, or at least the goal here is to set up a network that can do things arbitrarily, and by that, we mean that it will learn symbols. Symbols are arbitrary. Why A is A? Actually, we can use any other picture to represent the notion of A. There's nothing special about A, right? you can make C equals to A. It's actually fine. It's just that we grew up seeing A as A. Okay? So it's a symbol, all right? To represent some deep function that we cannot express otherwise. All right? Very difficult. All right? Okay, so this is the problem set. And we set up some parameters and we set up the variables that we're going to use. Let's talk about this thing here. And we have a vector, okay, I, which is in our notation, we are going to say that this is the ith layer, okay? And then, like this. Okay, this is going to be the kth node. Right? Remember, just like it's in Hopfield, we have the AI and then K, which is the K node. All right? And then similarly, here we have the F state. In Hopfield, I put the state on the here, right? But I'm, just changing it a little bit. Let's just put it there. Everything is neatly at the in the subscript. All right? And that dot means all in that range. When we put dot, rather than saying a specific k or a specific s or a specific I, it means all of the k from k0 to k last, and all of the states from state 0 to state last. Okay? So let AISK, all right, be the following, and by following I mean in the next slide, following input patterns, pattern vectors over k units and s states. Right? So we're setting up, we have that problem. Everyone agrees that therefore there must be some set of inputs, okay? A's of I's of K's of S, right? And what are these inputs? Well, in the next slide, that's the data table. Just like in Hopfield, we have a data table we want to solve, okay? That is A's of I of S of K. I'm going to set it up like this. All right. So S is every row. So we have state 1, state 2, state 3. Why did I write my 2 like this? State 2, state 3. So it'll be dog, cat, tree, mouse, house, telephone, car, any state or any item or any object. So it can be state of the environment. You are in the kitchen, you are in the restroom, you are on a bus, you are in an airplane, etc. All right? Any state. And the features or the nodes, okay? Each node's sensitivity to some characteristics in the state. All right? So if it's a cat, maybe you have a node that picks up that this has a tail, this is a mammal, or it has 2 eyes, etc. And again, let's work with binary information for simplicity. So this one has a tail, has 2 eyes, does not have leaves, does not fly, and what have you, right? And then maybe some other things. So a binary sets of words, etc., etc., etc. So you have a data table of inputs that you want to map to some desired output here. Let A of T dot dot over states over nodes, okay? Over nodes over states, be the target output pattern vectors over R units corresponding to each input state S. So that essentially it'll be R S. Okay. So now, similarly, we have a data table. All right. So if we had 1, 2, 3 here, so we had 1, 2, 3 here, etc. for S how many, and here I have, let's say, 5 or more K input nodes. I can have more or less, okay? Whatever it is, they have some output, okay? Similarly, this is the output data table. Note that the number of input nodes, K is input nodes, okay, is not necessarily the same as the output nodes. Okay, so this input, this is output. Because we already said it has to be able to map anything to anything. So there is no requirement that the output must have the same number of nodes as the input. Otherwise, it cannot be anything to anything, right? It could be you are mapping a 4-dimensional thing to a 2-dimensional thing, right? You could map a 4-dimensional thing to a 4-dimensional thing. That's fine too, okay? Which is like a Hopfield network, right? You have an 8-bit to a 16-bit to a 16-bit output, 16-bit input to a 16-bit output. Here, if you want to have the ability to do anything to anything, then you must relax that rule. You cannot have it that the input and output must have the same dimensionality, right? So you can say, I have 16-bit input, but I only want a 4-bit output. Or I have a 4-bit input, but I want a 16-bit output. It's fine. You're supposed to be able to do that, okay? So that's the input-output data table, all right? So then let's put that all together. This is the data problem, the data table, okay? 1, 2, 3, blah, 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 1, 2, 3, blah, blah, blah. And then we have, it's either zeros or ones. We keep things binary. So we have the input, and we have, note that this is the AT, this is the target or desired output over states over R, and again, 1, 2, 1, 2, 3. Okay, just to have a distinction that the input number of units does not have to be the same as the output number of units. It also let's restrict it to binary outputs for now. And specifically, we want to find some way of learning or embedding or encoding or mapping, strictly speaking, the input to the output target that we want. And we want to have an estimate of some mappings, which are the weights. And so essentially, that's the formal setup of the problem and the parameters that we have to work with, okay? Then what we are formally trying to do then is solve this W, you see how this is an estimate. We don't know it, but we want it. So we have to solve it. Solve W for A, that if the target output, okay, is some function over all states, okay, of whatever this W that we want and whatever input that we give it, right? We want to solve this equation, all right? For, and specifically we want to solve it for any sets of elements or all states of AIAT. This is the formal setup here. This is the very big goal here. Okay? If you sit here and then you look at this problem, you'll be like, you are asking for everything, right? Which is what we are asking of our LLMs and AIs, isn't it? We're asking it for everything. We are asking any question, give me the correct answer. That's really what we want. It's a very, very high goal. But this is essentially boils down to this kind of formulation, this formal statement. Okay? So like, wow, can you do it? All right, can it be done? I will draw it out, and then we will take a break. This is the proposal that Hinton gives, that yes, it can be done, and this is how we can do it, okay? Hinton proposes to use a multi-layer perceptron, and this is the architecture. So again, remember, whenever we approach neural network, boil it down to its three parts. Its architecture, its three aspects. Its architecture, its learning rule, updating rule, and its activation function. These three parts put together, you have your network. Okay? And we will describe it as such. It is fully connected. Okay, remember our single layer perceptron? Fully connected means every neuron is connected to every other neuron in a feed-forward manner. All right, in terms of its activity. The activity is fed forward through fully connected nodes, and such that you have K in your layer 1, K1 in the second layer. The number of units, okay, is in the first layer, or you want to call this layer 0, is K. In the second layer, you might have K1 number of units, and then subsequently K2 number of units. Eventually, you will hit R number of units in the output, the jth layer, the downstream layer, okay? So I and J, I and J, and I and J are always relative, upstream, downstream, upstream, downstream. So for example, you might have 3 inputs feeding into 3 hidden layers, another 3 hidden layer, and maybe you only have 1 unit output, and it can either be on or off, right, if it's binary, okay? So actually, let me be a little bit more helpful here. Let's not use K, because you guys have already known it, that if you want to solve all sorts of problems, not just linear ones, you need hidden layers. So we're going to call them H, layer H, hidden, okay? So if you think of it as upstream, it is I, relative to the J layer, okay? So that, oh wait, sorry. I don't want to get confused. It is the K layer, but it is the number of units is K, all right? But it is the H layer, which has K units in it. This notation sometimes gets very confusing. All right, it'll be clearer as we go, as I draw this out. All right, so we start. So Geoffrey Hinton uses the vector notation way to show, or I can use the vector notation way to illustrate what Hinton means. We have input. Multi-layer perceptron just means that we have a hidden layer 1, okay, and this is connected by the first layer, which is i's of k and h's of k, which has k1 number of units. All right, that's what I mean. All right, you have a h1 layer, and you have, oh sorry, I have to put a 1 here. Yeah, h1 layer has k1 units in it. All right, and you might have another, just to make it even more concrete, let's say you have another hidden layer, okay? Then we will write it as such. Okay, this is the notation. And then finally, you might have etc. H3, H4, H5 if you want, okay? But eventually, it would get into AJ. No, this is AJ in contrast to what we want, which is AT, okay? But let's deal with AJ first, and this will be H. If let's say it's just this layer, then this will be H2, K2 to J, R. Right? If it is HN, then it will be HNKN to JR. Okay? Hinton proposes this architecture. You do all of these feed forward, fully connected with however many units, and once you get to AJ, you evaluate. You have a function that evaluates AJ with respect to AT. Okay? So don't know what function it is first, but some evaluation of what AJ is and what we want AT to be. Okay? So he says set it up this way. We use a MLP architecture. So just to make things super concrete, let's assume that we have 3, 3, 3. What that means is that, let's say you draw 3 nodes here, 3 units here, okay? And these 3 units connected to this 1 unit, okay? And this will be A, I, K equals to 1, A, I, K equals to 2, A, I, K equals to 3, right? And then these are the weights, W, I, K equals to 1, H1, K1 equals to 1. W, I, K equals to 2, but H1, K1 is still equals to 1. Draw it out, 1. Okay? The notation is and the indexing is very critical here. So don't get lost. I will get lost. Right? But I hope you don't. I'll try my best not to get lost so you don't get lost either. Okay? But so in the first layer, when we are talking about one node in the H1 layer, we are talking that H1, K1, node 1, right, receives input from 3 nodes in the input layer, multiplied with the dot product of the respective WIK weights. Okay, then you could talk about here. We have another layer, right? So let's use another color here. Okay, and then we say we draw 3 units here. So similarly, because we said that the first input has 3 units, let's make the first hidden layer also only have 3 units. So similarly, we have AH, this will be AH1, K1 equals to 2, and this will be AH1, K1 equals to 3, right? This will be AH1, K1 equals to 1. This will be AH2, K2 equals to 1. And you can fill it up in your own time, but you get, I'm sure if you get it by now, that what this will be. 1 by AH2, K2 equals to 1. W AH1, K1 equals to 2, H2, K2 equals to 1, and WH1, K1 equals to 3, H2, K2 still equals to 1, right? Get it? Okay? And then finally, we have AJ, R equals to 1, and I'm not going to belabor this, but this will be, for example, this will be H2, K2 equals to 3, J, R equals to 1. That's the weight for this one, this weight. Okay? Hinton proposes this setup of a multi-layer perceptron architecture that can grow, that is flexible in terms of its hidden number of layers, and is also flexible in terms of the number of input and output units. Okay, with the idea of a fully connected feed-forward relationship, as illustrated by how each unit in the hidden layers, in the downstream layers, receives the weighted inputs from the upstream layer, one layer at a time, like this. Okay? At least as in the chapter. Obviously, we can do things more complicated, but in the chapter, let's deal with this setup first. The proposal is this will work. This will, if we have this and then we have plus the evaluation of the AJ and the AT, somehow this will enable this network to map anything to anything. Okay? All right, so this would be a good time to take a break, and we will come back and explore this deeper, and then it will get more and more mind twisting subsequently. All right? Okay, so let's take a 10, 18, let's come back at 10:30, 10-minute plus break, okay? 10:30, and we'll carry on from there. All right, let's continue here. All right, so we have a setup by suggestion proposal by Hinton that if we have a network that looks like this, fully connected, feed forward, and with a final output AJ, which you then evaluate with respect to AT. There's nothing in here that guarantees that it will do mapping anything to anything. That's the goal. Okay, it's just that this is a proposal. There is more to this proposal. He will show you how this works, or how we use it in a particular way. Specifically, what is the eval function here that will then make it work. Okay, so let's move on. So if we accept that, well, he proposes that architecture first, and then he talks about sort of the activation function, all right? Such that if you have the notes from the previous slide, I can't go back and forth, it will be too confusing. Such that if we talk about, let's say, one hidden layer number 1 and K unit, I'm not going to say equals 1, I'm just going to say K1, okay? That activity, that activation state of AH1K1, okay? Actually, let me do it a little bit more tractable. I'm not going to have it as, I'm just going to put it all flat, otherwise it gets very unwieldy. Is some function 1 of all the input, right? Dot means all of K to H1 K1. And the activation states of all the inputs. Yeah? This, no problem. Some function, we don't know what function yet, but let's call the function F1. Okay? And similarly, in the hidden layer 2, K2 unit, all right, is going to be some function 2, right, of H1 K, H1 all, K2, okay, and H1 all. No problem there, right? Because the second layer's activation state will be the weighted products, some function of the weighted products of the previous, the upstream input multiplied by the respective weights, and so on and so forth until we get to the output, all right? It's going to be some function, let's call it function number 3, of the hidden weights 2, all of them with the, with the J, R node, and such that this is all the hidden layer number 2's activation state. Okay. Now, if we, if you get all this, call this equation 1, equation 2, and equation 3, you'll see this describes a propagation, a forward propagation of activation states, activations. And in fact, it's a wave. It's like you put a ripple, you have a lake, it's a pool, it's still. Then if you touch one part, the wave of that activity gets propagated forward according to some property which is determined or constrained by W's, okay? And so that if I were some other part or location of the pool, okay, my state is going to be equals to this one, no problem. This is copying this one. But note, AH2, oops, why it's not yellow here? Okay, so we can put 3, put 2 into 3. So that this is going to be F2 This is some interesting AI. Wow. F2, yeah, then no problem there. H1, everything, H2, K2. And again, doing some fancy thing here. If you note this one here. So similarly, you can do F1, I, everything H1, K1. Right, yeah, okay. Then A, I, 1, 2, and 3. And if you are, if you see that the goal has always been to, for any input, you do something to it, and then you get some output, essentially, that is, you get A, J, R, okay, is going to be equals to, we have F3, F2, F1, let's call it one big function, okay, we don't know what it is yet, okay, but doesn't matter, it is some relationship that binds all of the input and hidden weights as one gigantic embedded matrix, right? An array that results from a previous array that results from a previous array from the very initial input. This is the multi-layer perceptron, essentially, all right? And what this term here can take whatever combination, as how many layers you want. The layers each has how many nodes you want. It doesn't matter. It is all just one big W that takes in the initial input. You feed it through. It gives you the AJ. And essentially, these are the LLMs, the CNNs, the DNNs. Just that they have very, very different complicated architectures, but essentially at a very formal high level, that's what they are, okay? Doing that. So they are all forward propagation of activations, just that because how you shape the architecture, the propagation goes in different ways. You can imagine it like, again, back to the pool, water pool analogy. If the pool is just a uniform circle, then you touch the center, the ripple will spread very evenly as a circle out, right? But if your pool has like rocks and uneven, then if you touch the center, it will spread, but certain rocks, whatever, will block it, so that eventually whatever wave that reaches the edges is going to look different because of the different structure of the pool. So this is the pool. This is your initial perturbation, and this is whatever you get at the edges, okay? So you can think of it that way. Any questions? All right, so Hinton went from here, this is the vector notation representation, to if you want to go equation-wise, this is the equation, okay? and you're putting 1, 2, and 3 in, and then he moves forward further. So recall, and this is the so-called the magical part. Recall that our goal, recall H naught, our goal, recall H naught, our goal, okay, which is to solve W such that delta, okay, which is equals to AT AJ approaches 0. We want to minimize delta, right? And as we expressed just now, AJ is equals to some big function of f h star AI. Okay, so we put that back here again, right? So we don't know what function f is, all right? But we know that it has to be taking in it has something to do with the weights, the W, okay? So we can say that dj with respect to the weights, wij, this is calculus differentiation, okay, is going to be equals to some generic derivative. So here, prime here means derivative, means you have some function, you take the derivative of that function. You have a g, and then you put a g prime, all right? And then this is going to be taking the input ai, right? That the change of the output with respect to the change of weights is going to be some derivative of the input, right? No problem? Okay? Okay. So then the trick is, or the goal here is, therefore, we want to find g of ai. G is not the derivative. G is the integrate, right? It's the previous, right? So g prime is the derivative, but we want to know g such that we can get this minimization of the delta, all right? So we want to find whatever this function of ai is, the a and the input is, such that this candidate function, which we will call e, as Hinton calls it e, all right, with respect to the change of the weights, implements gradient descent. This notion here we will illustrate in a bit, all right? But the idea here is that we have the aj is a function of the weights and the input. This implies that the derivative of aj with respect to the changes of how aj changes with respect to how the weights change is a function of the derivative of ai, okay? So therefore, if we want to solve, part of solving w, okay, means that we want to find a function, a candidate function of ai, such that whatever this function, let's just mystery quantity here, okay, which is candidate, whatever we think will work, okay, that how this quantity changes with respect to how the weights change is going to implement gradient descent. What do we mean by gradient descent? Gradient descent looks like this. That if I have changes in W, so this thing here, right? Changes in W, okay? Then this quantity, how this quantity changes is going to have to look like this, gradient descent. It can be a curve or it can be a triangle, it doesn't matter. The fact is that if I am on the positive side of change, so if my weights, W, change in weights, remember W is the change in weights. So if my change in weights is positive, okay, right, meaning I have to increase my weight, I want it so that by increasing my weight, I am making this quantity smaller, minimal, towards lower, okay? I don't want it to be bigger because what I want is to minimize, right? I want this, I'm going to make yellow, towards 0, right? So this is towards 0, right? So if my weights are on the positive side and I want it to go towards 0, which direction I have to go? I have to go this way, yes? If my weights are on the negative side, if I have to decrease my weight, right? I want the result of decreasing my weight is to increase the, go towards the right side of this function, which is also still to decrease the change in E, right? So if I'm on this side, I want to go this way, right? Because I want to have a minima here. This is gradient descent. So like if my weights are positive, when I change my weights positively, if I add it, if I make it stronger, it makes this quantity E go down. If I make my weights smaller, like by suppressing it, I also make my quantity E go down. So I want a function, right, that relates these two such that whether I'm adding or I'm subtracting, E always goes down. That's gradient descent, okay? And what function, what does this look like? It's not yet the function, but what this means is that we have to show that whatever E is, whatever this mystery candidate function E is, okay, what this is, okay, will result in this kind of quantity, negative. Why? Because if here I am in the negative, if I'm in the positive range of W and I put negative, then the change will be negative. If I'm in the negative, so I'm going left, I'm decreasing, right? But if I'm in the negative side of the change in W, negative of a negative is positive, so I have to go right, right? So if I put this negative in front of how this mysterious function change with respect to the change in weights, then I am making it a gradient descent. So in other words, gradient, I can make, if I can have a function such that its relationship as a function of the change in weights is a negative one, then I know that this function will achieve gradient descent. Okay, it will help me guarantee that my this mystery function, this quantity, will always be minimized with respect to the change in weights, and that's gradient descent. Okay, this is the core concept in Hinton's argument here. All right. And so that if that's the case, this means that what he wants to do is to show that as this function g prime, whatever this function does, okay, which let's call it E, the candidate, okay? And how that relates to how this function relates to the change in weights. This is very abstract. So how this candidate function, all right, relates to the change in the candidate's function with respect to the change in weights. is a negative 1. It's 0, okay? Like that. It's a negative slope. This on the right expresses this idea here, this very abstract idea here. Okay? Okay, we'll let that sit. But that's the notion of gradient descent. So we haven't shown you anything how that relates to the target output and the actual output yet. But we first have to understand that he is trying to tell us that if we want this network to minimize the error, okay, minimize delta, then we need some mysterious function, we don't know what it is yet, that if we make this network change its weights according to changes in this minimize function in a negative way, then this function's value will be minimized. Okay? That's the logic there. So then it remains, what is this mysterious function? Okay? And it's like a trick again, like these people always just pulls magic things out of their hats. It's like, what? So consider this quantity which we call E just now, which we don't know yet, okay, such that dE by dW is equals to, is the function of the inputs, right? It's not the derivative, it is the actual original function, okay? What we want is we want some E such that dE by dW is this function that we want to use, all right? And in fact, he uses a chain rule here. Note that dE by dW as a function of AI, all right, is whatever its output. This term here describes how the mystery function, okay, changes with respect to the actual output of the network. Okay, so we don't know what this mystery function is yet, but we'll come back to it as we talk about it clearer. But there's this mystery function. Its value will change as a function of whatever this network output gives it, right? That's this first term on the left. The second term on the right, what this network's output, how this network output changes is a function of the weights. As the networks itself, the weight is changing. You put these two together, you get how this mystery function changes with respect to how the network weights changes, right? This is how the chain rule is operating here. Does that make sense? Okay, so now this will make it a lot more clearer, is that we try a candidate function such that it is the sum of squares error, sum of squared residual, okay? This is from statistics. This is variance, right? Sum of square variance. But why? It's nice quantity because it is always positive, right? And it reflects the degree to which AJ deviates from AT, regardless of whether it's higher or lower. So we want to minimize E, right? That's essentially the same thing. And you don't ask me why. There are many other functions you can do, right? And this is really what we call the loss function. This is how much is lost, right? And we want to minimize loss, okay? So and moreover, this is delta, right? We said delta is the target minus the output, the actual output. And in fact, delta is part of this loss function if we construe the loss function as its square, sum of its squares over all the R units, and then just have it, because if you do this, so if we do this, correct? Then if we do dE, if implies that if you were to derive it with respect to some other quantity, it's very easy because it will just kind of cancel out. All right. Okay. So let's work this out. How does this play out? This is not proving anything. This is him just telling you that, hey, we find that if we have this term called dE by dW, we use chain rule, we get this nice way of splitting it up into its partial derivatives. In fact, I should write this more correctly. It should not be D, this should be partial derivatives. All right, this is more correct, okay? That therefore we can split this into the how this mystery function changes with respect to the output, and how the output changes with respect to the changes of weights. Put this together, how this mystery function changes with respect to the weights. And let's try a mystery function, which is the sum of square residuals, part of it which is incorporating delta in it. So then let's have these pieces, let's play it out, and then let's see what happens. That's how he does it. So let's write that equation again. We have dE, dW. So this is now math. Okay, this is just now all math. And let's take this first part. Okay, this first part, dE, partial derivative of E with respect to AJ. Let's expand it out. Okay, how does this work? We said that E is half sum of square R of AT minus AJ squared. Okay, just work it out. Take the half out. D by dAJ, AT, yeah, AT squared minus 2AT AJ plus AT AJ squared. Right, just basic arithmetic. Continue. Yeah, this is propagated. Yeah, if you work it out, you cancel it out, right? So it'll be 2AT is left with the minus 2AT here. And then we have the plus 2AJ. Bring the 2 down. That's it. Because this is AT with respect to AJ is a constant with respect to AJ, so it drops out, nothing. Okay? And then take it out. It is minus AT minus AJ. 0. Yes? Minus delta. And it's critical to appreciate it is negative. all right? Which implies that delta is equals to negative of if our loss, how our loss function changes with respect to how the output changes has a negative relationship with the delta, which is a gradient descent, right? We said if you have this quantity, not yet the weights, but it is with respect to the outputs at least, right? Is that if you have something that's bigger, you make it negative, you push it to be smaller. You have something that's smaller, which is negative, and you make it negative, you push it positive, make it positive, so that it becomes towards the center again, and then that instantiates already some initial form of gradient descent. Okay, but let's put it together because we have another term. Okay, so we have this term. Should I put it here? Yeah, let's do it in the box here. Okay, so let's say that for dAj, which is how the outputs change with respect to the weights of the network, note that Aj in the linear case, so let's assume that this neural network doesn't have any nonlinear activation function yet. It's just a slope. So that exactly Aj is exactly the input of the products of the input with respect to the weight. That is that the function f here, f, imagine that f equals to 1. All right, so that Aj is equals to 1 times Wij times Ai. Okay, that's the linear case first. If we take that f is equals to 1, then Aj is equals to W times Ai, which implies that dAj dW is equals to Ai. Correct? Aj is equals to Wai. Derivative of Aj with respect to W is Ai. Correct? Yeah? It makes sense. Linearly, if the relationship between Ai and Aj is a linear one, the function is f is equals to 1, then the derivative is the linear slope of the input, okay, which is Ai. So this is the linear. So now we have this term, and we have this term, okay? We can put it together, and I'm going to use a different color here, just to drive it home here. Okay, that therefore dE, is there no space? No, I think it will work, and I'll use a different color. This is too dark. Use this one. Okay, that dE by dW, okay, is equals to wow, this is really some cool color confusion that it has. Is equals to minus delta. 好厉害的 color. Or that delta negative gradient descent. Okay, so that I can go back. What was it? Delta AI is equals to negative dE by dW, right? And if that's the case, then with respect to the change in weights and the change in the loss function, it will be a gradient descent. So it's the Hinton is going forward deep and then get all these and then going back again to this whole part here. Okay? Okay. There's a lot of layers of this, and it may be there are certain key conceptual blockages. The first one being that this notion of gradient descent in how it relates to change in E by change in W. Okay? You just have to think about it in terms of the network. I want some way to train my weights such that the way I train my weights, okay, is going to make what I use to train my weights smaller and smaller. Correct? That's what this graph means. So that and what that means is that if the way I train my weights makes and then I find that this weight has to increase, then the overall, and note, E is like an overall total error, so to speak, okay, because E is sum of total errors, okay? And this is going to be, and I'll highlight this in a bit, okay, but E is like total error of the model. If I change this weight, this specific weight, Ij, that weight, adding this weight, making this weight stronger, I want it such that if I make this weight stronger, that it will lead the total error to drop a little bit, right? Or alternatively, the case where I have to make my weights weaker, okay, suppress it, or stronger in a negative direction, then I want it to also, my requirement is that in doing that, I also want to reduce the total error of the model. And that means I have to make my model go that direction. What kind of relationship will do that? It's a negative one with respect to how the total error changes with respect to how I change each weight. Okay? So that is the concept of gradient descent. But that means that my change in total error with respect to change in each weight is going to have a negative slope with respect to this mysterious function that I'm going to be evaluating in the first place. Okay? So what mysterious function will do that? He suggests sum of square residual, and it has this form, so that if we have this nice equation star, okay? 1, 2, 3, no, it should be equation 4 now, right? Equation 4. And so it turns out that if we plug in equation 4 into the partial derivative expansion of the change of the loss function or the candidate function that we want to minimize with respect to, the candidate function with respect to how the weights change, if we work it out, it turns out that the candidate function and how it's changing with respect to the weights will have a negative relationship, a negative slope with the delta term in the first place, which is right here. Okay. So his suggestion here is that if we make a network change its weights as a function of delta, the network will be doing gradient descent, because if you work it out, it will the delta is each delta r. Delta r is the deviation for each AJR unit with respect to each, that's why the r is there, okay? Which with respect to HATR unit, okay? That this will feed into the total error, which is E, the big quantity here, equation 4, okay? So that when we set up such that each unit's delta R, okay, is used to train each unit's weight, the total error will be reduced. That's gradient descent. That's how you keep thinking over and over again. The pieces will slowly fall into place. Okay? Okay, and again, as I always have to emphasize, you are not required to understand the proof or prove anything or know the proof. It's just helpful for you to know this is how Hinton arrived at. That's why we are all using error backpropagation, because of this, the fact that if you use it this way with the chain rule here, okay, this chain rule here, it turns out that the network will do gradient descent. And gradient descent is what we want, the goal, which is to minimize delta, minimize error. Okay, I'm going to move a little bit more and then we'll take another break, okay? Because here we are talking about, this is the linear case. Remember? The big function f is 1 here, where the function relating the input and the weights to the output is assumed that it is 1. What if we don't assume that it is 1? Function is not 1, is some nonlinear or complex class, a bigger class of functions. For example, the sigmoid function or the ReLU function, which is not linear one, okay? So it's a thresholded one. How does that work out? Here we show that in the linear case, you get this nice derivative such that the change in the loss function with respect to the change in weights is a negative relationship with delta AI. What if it is nonlinear? For nonlinear, function, okay, just to remind you that f is W AI, okay. We just have to note this, that right, this is putting it there, then delta is equals to yep, WAI. Oh, sorry. Sorry, give me a second here. DEWAI. I'm just going to write it out. I need to go back as to whether my notation here is correct, but it should be, okay? The change is with respect to the weights of the input. Yeah, okay. that the AT minus AJ is equals to the negative, because of the initial negative, and we just bring the AI down. That's what this is trying to say. Yeah. Correct. So we just move this to the denominator of the other side, and then DE is equals to the negative of D F of A I. So in the linear case, this one is F is equals to 1. If we want to have the inclusion where F can be nonlinear, well, let's just say that this term then, let's imagine it as a more generalized function F again. So we put F, WAI is equals to F, where F is not equals to 1, all right? And then equals to negative D, partial derivatives. J. And this is how Hinton does it in the paper, okay? There's actually a much easier way to do it, but I don't want to, I'll just go through the way he does it in the paper. Sorry, because it's a function, I have to put the comma there. Okay, it's not a direct product, but it essentially is. Okay, so that simply, so we expand it into the partial derivatives, okay? But then simply di by df of w a I, oh sorry, ej, right? Yeah, j. How the output changes with respect to this nonlinear function that takes in the original input and all the weights of the model is going to be f of prime here, not 1, okay? This is f prime, so please don't be confused. Is some derivative of the function, right? Because this is the derivative of how the output changes with respect to the input. That is the activation function, f prime, that takes in the pre-activation states. Okay, I'll draw this out in a bit, all right? And then applies a threshold to it, okay? And then makes it whatever AJ, therefore the output, the binary output should be, all right? And so we have that, this is this term, right? So this term is this term, okay? Then we have this term, DE, sorry, delta E, delta AJ, okay? So which is this term, okay? Is equals to AT minus AJ, right? How the error changes with respect to output is exactly as we said, it is delta, all right? So this, putting this together, implies that delta is equals to AT minus AJ. In the nonlinear case, f, small f. This is the nonlinear case, and in the linear case, this was AI as linear. Okay, so for example, now let's give you. Wow. Okay, it's doing it again. okay, where f of w times ai is a sigmoidal function of w times ai. So it's like that's the activation function. Okay, such that f prime okay, so if you know the I believe the sigmoid function, I think I have to look it up. Please don't hold me on that. I my notes later. But the derivative of the sigmoid function is very easy. It's just a times 1 minus a. All right? Where the sigmoid function originally is e to the ai w, something like that, right? Something like that, right? That's the sigmoid function. If you take the first derivative of the sigmoid function, you end up with a 1 minus ai. Okay, so then the delta in the nonlinear case is going to be just that, the unit, but modulated, the same error delta, the original delta, but modulated by, some nonlinear function of the inputs, weighted inputs. That's all. So the linear case is already negative. The nonlinear case is going to have the same thing, except that the delta in this case is just modulated by the activation function, or the derivative of the activation function. Okay? Excuse me. All right. So I am going to, is this a good face? Yes. Let's take a 5-minute break, and then I will continue on to how this is. We are going now leaving this very abstract proof world and going into now the actual model which we will be implementing in the code 2 weeks later. But I want to highlight the key equations and the key things to note that we'll come back again. We will be needing this when we talk about the code. Essentially, first, note this is AJ. So this is output layer. So we have a delta for the output layer. But what about, so in other words, if we go back to that vector notation representation here, right? This is AJ. This is the output layer. So that eval, what eval do we want to do? Eval is going to be equals to AT minus AJ, and then AH 1 minus AH 2. That's essentially what I just showed you in the nonlinear case, just putting it here, that this eval function, this loss function that we want, essentially is this one. And that if we use this loss function and then we somehow integrate it to the weights, how we update the weights as a proportion of this loss function, that this whole network will be doing gradient descent. That's what Hinton is meaning here. Okay, so this is talking about AJ, the output. But when you talk about that, where hidden nodes, there is no output. It's not AJ. So what do we do there? Okay, and we will come back and talk about that more later. So let's take a 5-minute break, and then take a breather, and then we'll continue on. All right. Okay, guys, let's quickly finish up. Then you know, there's a lot of stuff happening, and you all need time to digest. But you know, we can also continue in the next week. But I just want to cover up to this point here, at least in terms of implementation. At least touch a bit on implementation. But before that, just to highlight that if we've come to the point where we have we've shown that if we use the loss function as the you know, some quantity to do with delta, which is at minus aj, the network does gradient descent. And if that was in the linear case, and in the nonlinear case, we just simply have to say that delta is still something to do with at minus aj, but just modulated by the activation function's derivative, okay, which in this case we will be using sigmoid function, and the derivative of the sigmoid function is very easy. It's just a times 1 minus a. But in doing this, you note that because the loss function is initially defined with the final output, aj, with respect to some target. And so we have this delta that we have at the last output layer that we can then use to adjust the weights so that we achieve gradient descent, okay? The whole core is that if we adjust our weights as a function of this loss function, the network will achieve gradient descent. Well, we have this quantity that we got from the loss function at the output layer. But we note that Hinton proposed that, well, you know, this can be applied in networks with hidden layers as well. In fact, that's the key point of it, is that we can apply it in the hidden layers. So how do we get a sort of a delta quantity, but in the hidden layers when there's no actual AT, right? Because we have an AT for the final output. We know what we want our output to be, and so we can compare AJ relative to AT. But we have no so-called target hidden state that we want. We don't know that, right? So how do we do that, okay? And so this is for output layer. So for output layer, and you will see that in the model, when we implement it, we will have two types of delta. One is for the output, which very neatly has comparing the output, actual output, with respect to the desired output. We can define this very easily. But for a hidden layer, we don't have a AT to speak of. So what kind of delta can we compute for the hidden layer? Well, for the hidden layer, I'm just going to take this. It's just going to be for hidden layers, okay, because there could be more than one. We have the sum of the R output unit or the downstream, okay? And this is the nonlinear function, okay? And in this case, because we know that the nonlinear function will be an activation function, and the activation function essentially is taking the pre-activation state, which is the product of the upstream input multiplied by the weights, right? And then you apply the nonlinear function to it, all right? So how the loss function changes with respect to the nonlinear function, or in this case it's aj, right? Okay, or subsequent state. Oh, I should always use the correct one. It shouldn't be d, it should be the partial derivative. And this is aj. Okay? We'll just work this out first, and then you'll see. input, okay, times d of dAj. I'm going to change this form at the end here. Sum over k, all right? But so here is where the notation is very critical. So we have the input, and this is also input here. All right? And this is going to be equals to minus r dE by dF, same thing. The weights from the output layer. And this one will be R. This is just a mathematical form. So that hidden delta is equals to sum of R, delta of R, weights and you note that I reversed the R and the J. It's the jth layer with the rth node. Here is the rth node backwards to the J layer. It's significant. Okay, it will make sense when we draw it out. We may not draw it out today, but we can draw it out in the next lecture. Okay, so that so this is the hidden delta, delta H, as opposed to delta J. Delta J is very easily target output minus actual output modulated by the activation functions, okay, that we used to transform the input, the weighted inputs. Delta H is something to do with the output delta, okay, but modulated by the weights that resulted in that specific delta for that specific node. Okay, modulated by that, and then modulated by the activation function. So in other words, actually, the hidden deltas are the output delta, but then weighted by whatever weight caused that output delta. So that if you appreciate this here, for the feed forward, put a note here. Activation phase, we go from I to H to J, all right, which is going from K to K1 to R, okay? But in the feedback prop, and this is the back prop case, we go from J rth node of the jth layer to the k1th node of the h layer to the kth node of the ith layer. Actually, we don't need the kth node of the ith because we don't have error for the input. Okay, but there's this direction where we first propagate, feed forward the activity, calculate some delta, right? Then the delta R is used to feedback to get the delta H's. And the delta H's are used to update the weights of the hidden layers. Okay? So this derivation is just to show you that the hidden deltas are nothing but just the original delta, but then because the original delta at the output was caused by the feed-forward weights, right? So we take the original delta, and then we want to compute now I'm the hidden layer unit delta, right? I want to know what my delta should be, but I don't have a target to compare with. So I take what was I caused that hidden unit, I caused that final output unit, that amount of delta. So because I have a particular weight to that unit. So I take that delta, I then sort of dot product it backwards with the weights that I have with that unit, and that is my delta. So my delta is a reduced or proportion of the original of the actual delta, of the output delta. Okay? So that's what this term shows. This one. All right? Okay. This will become even clearer as I now go through some of the concrete implementation steps, which I will rehash again next week. But I just want to put this out there so that you can think about it and understand it, because I think when things are more concrete later on as I show you, all those theoretical things will be a bit clearer. Okay? So first, I'll have a pseudo, this is what we call a pseudo implementation, okay? Backprop. What I mean by pseudo implementation is that I'm not implementing it. You want to implement it, you have to code it. But I can tell you conceptually how we will be implementing the theory up there. Okay, so it'll be number one, specify architecture of your multi-layer perceptron. Okay, e.g., you say it's feed-forward, fully connected, and whatever, 10 input, 8 hidden, 4 output. Or, okay, 20 input, 4 hidden, followed by 10 hidden, followed by 4 output, etc. Okay, whatever architecture you want in terms of how many units in each hidden layer in the output and the input layers. All right, and specifically, you can draw it out. You can have your vector notation like this, right? And then you can have it like this. And then you will say something like this is a 10 by 1 vector. This might be an 8 by 1 vector, or this is a 4 by 1. So therefore, this WIH is going to be 10 by 8, right? And WHJ is going to be 8 by 4. Okay? So when you specify it like that, you know absolutely in your code you're going to need these variables. You're going to need an AI, an AH, an AJ. You're going to need WIH, WHJ, and their sizes accordingly of these arrays are going to be like this. Okay? So, and if you care, you can show that it's going to be like that, right? The shape. So, you know, you can have many different shapes. Of your MLPs. They can take different, and you will see it's very interesting because this will obviously determine the performance of your network, like how many degrees of freedom at each layer, which determines therefore how much information gets propagated forward and how much information gets propagated backward. This is a very much higher level stuff. So anyway, step 1, specify the architecture like so. Then step 2, specify the learning rule. And we've spent so much time going through the theory. We know basically that the learning rule has something to do with delta rule. Okay? Specifically that, as we said, we want a learning rule based on a loss function, with the loss function being the delta function, okay? Such that if we use the delta function to train our weights, to change our weights, then the network will do gradient descent. So we want to change our weights in the backprop way, okay, at time t plus 1, the next iteration, okay, not the current one, the next one. The next update is going to be equals to, this is the eta. Eta is the learning rate. You'll see in a moment how it comes in, but I'm just put it here first. And this is the delta J of state S. Remember, we have many different states, and in correspondingly the inputs S. This one is alpha, and it is the momentum. Okay? These are scalars, by the way, meaning that they are just one number. Okay? They are not a vector. All right? At time t. Okay? And eta ranges from 0 to 1, and so does alpha, and such that eta plus alpha equals to 1. In other words, that they are counterbalancing each other. Okay, so let's unpack this a little bit. All right? And so this, because it's j to I, this expresses backprop. Very key concept. The change in weights only occurs in the backpropagation phase. In the forward phase, there is no change in weights because whatever weights you have learned, you use it to generate some output. You then compare the output with respect to your target, then you get this loss function, which you then used in the backprop phase to change your weights accordingly in the hopes that it will achieve gradient descent. Okay? Meaning by doing that, your loss function will be minimized. If you use the loss function to adjust the weights in the negative gradient descent way, your loss function will be minimized. Okay? So that is this learning rule here, that you want to find this change in weights at the future iteration. This is going to be, first let's talk about the right side part. This is going to be added to the prior time change in weights, right? Yeah, because I learned already and then I do it again and I learn the next time, I do it again, I learn next time. So you change from relative to the previous update, okay? So that's these parts. The delta here, no problem. This is the output delta, and we showed that it is delta times the AI, the input, or the function of the input, right? The activation function of the input. So these two terms, no problem. What about eta and alpha? Now, eta is the learning rate. You can imagine, and it ranges from 0 to 1. So if eta is 0, let's say if eta is 0, your weights never change. Your weights are always the previous weights, right? So, and if eta is 1, then your weights completely change as a function of whatever new update the delta gives you, right? Delta is completely determining the change in weights. So learning rate means it learns faster from new information. Okay? The closer it is to 1, the more completely the new information is represented. If it is less than 1 but greater than 0, it means the new information is kind of discounted first, okay, before it has a chance to affect my subsequent weights. So that's learning rate. What about momentum? Momentum, you note, is a adjustment for the previous weight. So it is kind of like a dampener, hold you back. If momentum is 0, means my previous weight, I don't care what my previous weight. I totally just update according to the new information. But if my momentum is absolutely 1, then my new weights will have some contribution from the old weights by a complete factor, right? I have complete memory of my previous weights. Or I can discount it. I can say it's 0.5. So I don't want it to learn. I don't want it to completely not learn, but I do want it to also hold something from the past as well. So that's what momentum does. Okay? So the update in the weights in the backprop phase is a summation of the previous weights weighted by momentum and the new incoming delta information, because we want to do gradient descent, but weighted by a learning rate by some factor as well. Okay? So then we have the architecture, we have the learning rule, and finally we have the activation function, step 3. Okay, and we said that this was some mysterious, what is this F? And I said just now, it's the sigmoid. Hinton applies the sigmoid, but you know in current LLMs they use ReLU, and you know, you can use whatever else. As we went through in one of the initial lectures, there are many, many activation functions. At least in the exercises, we will ask you to implement the sigmoid function as Hinton did in the chapter. And it looks like this. So we have theta, and then we have 0, and then we have aj, which is the f of wai, right? And then we have 1, and we have 0.5. And it sort of looks something like this. Never reaches 1. It crosses over at theta. That is the sigmoid function. And therefore, the derivative of is equals to, I'm not going to work out the math. If you want, you can. I assure you this is the answer. And this is if you use input, but similarly, because we will be using it for the output, so actually it'll be, oops, it'll be 1 minus output. All right? Yeah, because it's about the derivative of the AI times W, so it'll be that. I to J, I to J. Okay, yes. Okay, so these 3 components. Any questions about these 3 components first? Because that's really more important for you for when we want to implement it. We have the architecture, whatever it is. Okay, when we do the coding, we are going to have all these variables, AI, AH, sorry, right, too horrible. AI, AH, AJ, WIH, WH star H star if you have more hidden layers, and finally WHJ, right? And you have the dimensionalities. This is your network. Your network consists of this architecture, okay? And then you have your learning rule, which is these W's. Change in these W's is going to proceed according to step 2, okay? And the AIs, which are here, the A's, okay, are going to change activity as a function of this sigmoid function. Okay? All right, I think that's a lot. So the rest of it I will cover again the next lecture, because next phase will be to put all of these things together in this pipeline, which I already sort of drew a schematic. This is the pipeline. Backprop MLP pipeline. which is that we will first do a feed-forward phase. Then, according to all those A's and W's and activation functions, and then we will calculate delta. Then we will do a backprop phase, one time for the output layer. Then and from the output layer, then we can get the delta for the input layer, and then apply the learning rule, the change in weights. And then we will do feed forward again. And then we will do evaluation, then output, hidden, and then change weights, and then feed forward. This cycle, this pipeline will keep going on and on and on. And miraculously, how this network will perform will be it can learn to map anything to anything, as long as you keep doing that. Okay? Or at least that's the claim. All right? Okay. So yeah, so for this class, we just talk about things at relatively abstract level and theoretical level, but we do kind of move a little bit into sort of a bit more concrete. So hopefully if you see how this pipeline goes and all these components, you kind of arrive at a clearer understanding of why the theory is the theory, why it works that way or how it works that way. Okay, and then again, as always, I think we can talk a lot about concepts and theory, but the best thing to do is really to just implement it and try it out, and you'll see. As when you do the code, you see how the numbers get spread out or get used, and then it will make better sense that way. Okay? Okay, that's a lot to consume. Any questions? Too many questions. Okay, so the videos are there. You can go back and revise and think it through. Yes, I think this is not something you can just immediately grasp just like that. Okay, you have to think it through. I also do have an AI version of this. Maybe the AI version, which is a bit more brief, might be simpler, but it is according to the Hinton's way as well. And that might be helpful. I'm gonna vet it first, then I will share it with you guys. Okay, just always be careful about how AI says things because it might be hallucinating. So I do think that it makes a nice case, but I want to vet it first before I share it with you. Similar to, it's actually exactly the same. It's just, it has a slightly different angle, just a little bit different angle, but it is very, very similar. Maybe it might be helpful, okay? But I'll post it later on. Okay, so if not, or if you're too busy thinking about it and you haven't crystallized your thing, which is fine, but then in that case, let's call it day for the formal class. And if you have any questions, you can ask me. I'll still be here. And then, so just remember that please be working on assignment 1. I believe you can do it easily, right? Because we've provided enough guidance. But do work at it, and then although it's due on May 15th, if you can hand up, within this time, and since you have a break next week, please do it, because when you work on assignment 2, it will be harder. And then when you work on assignment 3, it will be even harder. Okay? So we want to clear it out. Each of these will get you deeper and deeper. You will have the necessary tools to do it because you get into the cycle. All right? But you do have to be on the ball, on top of things. Okay? All right. So thanks for today, and then we will see you in a couple of weeks' time. Okay? All right.